Hello everyone, and welcome to my talk about the experiences of adding SYCL acceleration support to GROMACS application. My name is Andrey Alekseenko. I am a postdoc at KTH Royal Institute of Technology and SYCL Lab in Stockholm. This talk is prepared together with my colleagues, Dylan Pal and Eric Lindahl. As some of you might know, GROMACS is a molecular dynamics engine, one of the most widely used in the world. According to a 2018 HPC market research, it accounted for 5% of worldwide supercomputer utilization. But besides supercomputers, it runs on smaller lab clusters, standalone workstations, and even laptops as part of the Folding at Home project, achieving high performance on both CPU-only and heterogeneous CPU plus GPU machines. For that, GROMACS has to support a wide range of hardware and software platforms, multiple CPU architectures, all major hardware accelerators, all mainstream operating systems and compilers. This is not only a theoretical portability. We have our CI run regular tests on more or less mainstream configurations, and thanks to the inclusion in Debian and other Linux distributions, GROMACS is also tested on more exotic hardware like IBM System Z as part of their infrastructure. If we look closer at the codebase, GROMACS is written in modern C++17, although, as with any software with 30 years of history, not all parts of it are as modern as we wish it to be. The code uses multiple layers of parallelism, from manual SIMD to parallelize data processing on a single core, to shared memory multiprocessing with OpenMP, to GPU offload for highly parallel tasks. And finally, there is MPI for inter-process communication. All in all, it amounts for nearly 500,000 lines of C++ code, as well as thousands of lines of GPU-specific code, many of which are duplicated and are currently targets of our focused refactoring effort. Now, what exactly are we accelerating? Here is a schematic representation of an MD molecular dynamics main loop. First stage, shown in blue, is in a way preparatory. We reassign particles to different domains, which is necessary for multi-node parallelism, and update the neighbor list. It is done every 100 or so iterations. The core of the loop is the force calculation. Given the particle positions, we compute forces between them. Different kinds of forces can be computed in parallel. Then we reduce the result to get the total force for each particle, and finally we integrate them, possibly with constraints, to get the new updated positions and the velocities of the particles. The typical time step for biological MD is 1 to 4 femtoseconds, which means that a single iteration of the loop accounts for a few femtoseconds of simulated time. The biologically interesting processes happen at the scale of microseconds. Thus, we need to do billions of iterations of this loop, which puts strict requirements on both the throughput of the algorithm as well as its latency. Hence, runtime and hardware-related overheads must be avoided. To achieve that, we need to depart from a simple textbook MD loop depicted on the previous slide. Here is an example of one of the possible schedules used in GROMACS. We want to have the largest overlap possible between computations on CPU and GPU to reduce stalls of either. For that, we have a manually tuned separation of workloads between CPU and GPU with dynamic load balancing to do runtime fine-grained tuning. The horizontal arrows here indicate the sequence of tasks on CPU or in a single GPU stream. Solid gray lines connect the tasks run on each iteration, while blue dashed ones indicate the path taken on steps doing pair search and domain decomposition work. The vertical solid arrows indicate data copies between CPU and GPU, while dashed arrows indicate MPI communications. Bold dashed arrows show the tuning knobs of the dynamic load balancer. We can equalize CPU and GPU loads by tuning the trade-off between non-bonded pair and PME force calculation, and we can reduce GPU stalls due to pair search at the cost of more rolling-prone work. When running on multiple nodes, we have two distinct kinds or localities of interactions: local, between particles belonging to the current domain, and non-local, with particles from the neighbor domains running on different MPI ranks. The non-local interactions are much more time-sensitive because we must first receive their coordinates via MPI and then send back their forces to avoid stalling other ranks. For GPU offload, currently GROMACS supports 3 backends: CUDA, OpenCL, and SYCL. Until recently, only CUDA and OpenCL were supported, with OpenCL having less features but supporting more hardware, primarily AMD and Intel GPUs, although we have a limited NVIDIA support via OpenCL as well. In general, OpenCL is great. It's well-established open standard, supported to a larger or smaller extent by all major accelerator vendors. Unfortunately, its separate source model and the use of C99 make it hard to nicely integrate with the rest of our codebase, which is C++. So, while we could have continued to use OpenCL, SYCL is a nice alternative that can be used to target Intel and AMD hardware and doesn't have the drawbacks of OpenCL. Furthermore, while originally developed as a wrapper on top of OpenCL, now SYCL supports other GPU backends like Clang CUDA via both DPC++ and hipSYCL, ROCm via hipSYCL, and Level 0 via DPC++ and indirectly hipSYCL. So SYCL promises even more portability. Based on our goals, we focused on Intel's DPC++ to target Intel GPUs and hipSYCL to target AMD devices. Targeting NVIDIA hardware with SYCL is of low priority for us, given the existing, very feature-rich CUDA support in GROMACS, although it is possible through both DPC++ and hipSYCL. Speaking of the required version of SYCL standard, the features included in SYCL 1.2 are not enough for our use case. GROMACS already has highly optimized OpenCL kernels, which use subgroup shuffles, floating point atomics, and other features only standardized in SYCL 2020. Dropping them and the associated performance gains is not an option. Since the final version of SYCL 2020 standard was published only recently, actual SYCL implementations diverged from it and from each other, so we had to add a thin compatibility layer to support both DPC++ and hipSYCL. As an example, the subgroup voting function is called AnyOfGroup in the final SYCL 2020 standard, but DPC++ and hipSYCL call it AnyOf and put it in a different namespaces. As shifts, which in CUDA and OpenCL are called shuffles, the situation is even more convoluted. DPC++ calls the function shuffleUp, consistent with CUDA and OpenCL terminology, while SYCL 2020 has it as shift-group-right. hipSYCL, at the moment, lacks this functionality, although it can be implemented by calling native CUDA and hip intrinsics. But that is only a minor problem, since the functionality is there and the discrepancies in function signatures can be solved with a thin wrapper. The most obvious difference between OpenCL, at least the widely supported subset of it, and SYCL is the use of C++. Previously, with OpenCL, we had to use C kernels in an otherwise C++ codebase, which required us to duplicate headers or clutter them with preprocessor macros, and duplicate some of the utility functions, like array indexing helpers. And, in many cases, like the one shown here, the code in C++ is much more concise, while still allowing the removal and branching at compile time. But in some cases, like choosing in compile time whether to allocate the local memory array of integers or a float to, the SYCL code is more convoluted than the OpenCL version, although it is debatable which one is more straightforward to read and to maintain. However, this, again, is mostly trivial busy-work. Bigger issues lie in the GROMACS architecture. The GPU offload was originally written for CUDA. Later, OpenCL was added, with an abstraction layer allowing to reuse some code for both frameworks. And on the first sight, most GPU frameworks have very similar logic to them. You initialize the device, allocate memory, copy data, launch kernels. In that sense, adding SYCL alongside CUDA and OpenCL should be straightforward, just changing the name of the functions. But it's not so easy. If we look at some of the ideas embedded in each GPU framework, there are major differences. Luckily, SYCL inherited a lot from OpenCL, and we already have OpenCL in GROMACS. So, for example, our timing code could work with both regions, as offered by CUDA, and single events, as offered by SYCL and OpenCL. Same for the device selection code. Automatic resource management in SYCL is a welcome change, which only simplifies things. The native float-free type being either padded or unpadded is an issue we sidestep by using our custom fixed-size type as much as possible. The big differences are in the way scheduling and synchronization are implemented. CUDA, at least the way it's used in GROMACS, has in-order queues with various synchronizations. One inserts an event in queue, and when one later synchronizes with this event, it is guaranteed that all the tasks preceding the event are complete. OpenCL also has in-order queues and barriers. SYCL, on the other hand, implicitly constructs DAG, directed acyclic graph, of data dependencies between different tasks, and offers a native way only to wait for a single task to complete. In theory, data dependency-based scheduling is great. The runtime can automatically run different kernels in parallel, synchronize them, etc. We avoid bugs caused by forgotten synchronization. They avoid unnecessary waiting for the previous task if the current one does not depend on it. And that's not just theory. In one schedule in GROMACS, disabling some of our manual synchronizations and letting Intel's DPC++ runtime to do the scheduling improves the performance by 7% by eliminating an unneeded wait before data copy. Highlighted, we can see that GPU stalls in the bottom plot when an explicit synchronization is used, while it is working non-stop in the top plot when we rely on DAG scheduling. We are still looking at this issue, and likely it can be resolved by adjusting some conditionals in the code. So, this slowdown is probably not an inherent limitation of explicit manual dependency management, but it does show the power of DAG-driven scheduling even for an already optimized codebase. That's not all solved well. In GROMACS, we have a large existing codebase with very convoluted dependencies, which often rely on the queues being in order. While in many cases we use fine-grained explicit synchronization, sometimes we do rely on the order of the task submission. With regard to SYCL, this has two downsides. First, for the dependencies of GPU tasks, the SYCL runtime does the scheduling, so if we add more synchronizations, we are duplicating the work of the runtime, possibly in a less efficient way, as showcased in the previous slide. But the SYCL runtime cannot track the dependencies of CPU tasks, and it brings the second problem. If we have implicit dependency between two copies, due to the way they are enqueued, and we later wait for the second copy to finish, in CUDA and OpenCL, we are guaranteed that the first one is complete too. Not so in SYCL. We need to keep track of all the events associated with tasks to ensure correctness. Another downside of DAG is that we often do want to have a specific order of execution, even if no direct dependency exists between tasks. For example, in our schedule here, the critical path is non-local force calculation, shown by the red arrow. We need to compute the non-local forces and send them to our MPI peers as quick as possible to avoid stalls. To do that, we rely on a specific order of submission of the kernels into the queues. In SYCL, we can add explicit dependency between two tasks, but that requires extra handling within already complicated scheduling logic. And finally, different paradigms introduce differences in the scheduling logic between CUDA, OpenCL, and SYCL, which is a maintainability burden. Concurrency bugs are nasty, and the more uniform the code is, the easier it is to avoid or at least detect and fix them. So what did we end up doing? As a short-term solution, we decided to continue using CUDA-like scheduling, inserting a barrier event to wait for all the preceding tasks to complete. This cannot be done in a standard way within SYCL 2020, not unless we want to synchronize with the stream here and now, so we have to rely on non-standard features of our chosen SYCL implementations. The Intel's barrier extension, which is similar to CLNQ marker, and the ability to use native heap functions in hipSYCL. This is not optimal and not idiomatic for SYCL, but it works, and it allows us to have an identical logic in all three supported GPU backends, making the porting much easier and aiding future maintenance. Long term, we need to find a better way. It is unlikely we can completely ditch in-order queues, but we also don't want to do redundant work of managing task dependencies when the language runtime already does that, possibly in a more efficient way. DAG, the way it is implemented in SYCL now, has its limitations, notably the lack of prioritization and the limited ability to directly manipulate the graph and integrate into it the scheduling of host tasks, such as MPI operations and CPU kernels, but it is certainly promising. We need to balance all the considerations outlined, and we are yet to find a satisfactory answer. When it comes to portability, the problems are not limited to different function naming I mentioned earlier. When SYCL work in GROMACS started early fall last year, we first focused on adding a basic feature-limited support for Intel GPUs via Intel's DPC++. hipSYCL was kept in mind but not actively used. Later, we began working on targeting AMD devices via hipSYCL to ensure that our code is actually not theoretically portable. We already had OpenCL kernels optimized for AMD devices, and porting them was relatively low effort. We also had to deal with minor issues like clashes in global namespace, build system quirks, and so on. All in all, getting the code to compile and run was not a huge undertaking. Getting it to run fast, on the other hand, is a problem we are still tackling. The performance of Intel GPUs using DPC++ was similar to the OpenCL version out of the box. With hipSYCL, less complex kernels have performance on AMD devices similar to their hip OpenCL counterparts. But more complex kernels, despite using the same algorithm and in the end the same device backend suffer from significant performance regression, which we are still trying to resolve. In conclusion, for us, SYCL delivers on the promise of being the portable standard able to target different vendors and architectures. There are minor tweaks needed, and if we talk about complex kernels, one cannot avoid having to write specialized code for different hardware. And even with this specialized code, there are occasionally some major performance regressions from OpenCL to SYCL on simply identical algorithms that we are still investigating. As for the code, being able to use C++ for both host and device side is a welcome change. While OpenCL 3.0 has C++ support, not many vendors support OpenCL 3.0 itself. And the whole logic of the SYCL API is similar to OpenCL, which is a good thing for us. However, the particularities of GPU scheduling and synchronization are drastically different between CUDA and SYCL. For now, we resolved it by emulating CUDA style with SYCL, but this is kludgy and still can cause issues in the future. As a speculation, having the ability to explicitly manipulate the SYCL dependency graph in a manner similar to CUDA graphs might be a solution. Being able to set task priorities would also be useful for us. As for the other notable things, it's great that, since SYCL is implemented on top of other GPU backends, a variety of existing tools can be used. No need to wait for dedicated SYCL-specific debugger or profiler to appear. That said, the usability of OpenCL profilers vary. Next, complicated compilation process, usually with multiple compiler passes over the same file, is rather slow in both DPC++ and hipSYCL, especially when one has over 100 templated flavors of a kernel in a single translation unit. And finally, the SYCL ecosystem is evolving rapidly. The chart of implementations from Chronos.org I showed earlier is already a bit outdated. The SYCL community is vibrant and growing. We can expect more amazing SYCL things to come in the near future. In conclusion, I would like to thank Intel for funding my work on this project, Henrik Berghurst and Roland Schultz from Intel for their help in stimulating discussions, and the whole GROMACS development team, in particular Mark Abraham, Paul Bauer, and Artem Zhmurov. If you would like to learn more about GROMACS, here are a few resources: the main website, our developer mailing list, and the GitLab, where all the action happens. The SYCL-enabled version of GROMACS can be downloaded from our website, although I strongly recommend getting the most recent source code from our GitLab. And if you want to learn more about the algorithmic side of things, here is a recent paper, Heterogeneous Parallelization and Acceleration of Molecular Dynamics Simulations in GROMACS. Thank you for watching this talk, and have a great day!